Okay, just want to run over quickly, review here, guys, a couple of things about law of conservation of energy, work energy theorem, and then I want to finish the worksheet we started yesterday. It does have two sides, okay? You guys were only working on the first side of it yesterday, okay? We'll be finishing up hopefully the second side of it, which is pretty much the same stuff. And then next week on Monday, we're going to have the energy conversion lab where we'll set up the rubber bands and everything again, except this time we're going to shoot these little carts out with them, okay, and figure out how much of the work we do actually gets converted into useful energy, okay. And then on Tuesday, kind of related to that, you'll be talking about efficiency, all right. So when we're looking at how efficient, or the day before in the lab we're converting energy, the next day, Jack, we will be looking at how efficient that was. On Wednesday will be your unit exam review day. All right, so we'll go over what kind of stuff will be on the test. You'll get the review package. It's got, old exam problems on it and an outline and whatever else for you. Okay. On Thursday, we'll kind of finish up energy conservation of energy review, anything that needs to be kind of gone over. And then Friday, we'll probably start the next unit. Right, and then on Monday, you have your test. All right, your unit exam. So it's coming up quick. Okay, make sure you've already started looking over the stuff from the beginning of the unit. Okay, especially things like graphing. Right, that was one of the things we struggled with. Graphing and work energy theorem are probably the two things that will need the most review from everybody. Okay, prior to the unit exam. Are you guys done there? Because that's just weird. Okay, all right. Things to remember here. Okay, work energy theorem and law of conservation of energy kind of go hand in hand. Once you have done work, that energy will always be in that system until that system does work on something else. Okay, now for us, we don't ever really worry about the work it does on something else. We just worry about, I've put this much work in, and now there's that energy in there, and that energy is going to stay there. Okay, so we talked about the work energy theorem, where work is a change in energy. Okay, and that could mean often that force times distance equals one of the two kinds of energy. Okay, always final minus initial. Okay, is that ringing a bell for everybody? Okay, or it could be the potential energy version of that. Okay, and what happened most of the time to the initial energy in the questions we were doing? Usually it was 0. Okay, very few questions that we had were you actually given a value that would allow you to calculate what the initial energy was. So it started from 0 and went to some other number. Okay, so essentially work energy theorem, at least mathematically, broke down something like this for you. Force times distance equaled either kinetic energy or it equaled potential energy. All right, so those are some of the problems that you've encountered over the last little while. The newest thing, obviously, is that EI equals EF thing. Okay, the law of conservation of mechanical energy. Whatever energy is in a system stays there. All right, and that, we said, the prime example of that was a roller coaster. Okay, so let's do this question here as an example. So write this one down, guys, somewhere in your notebook as an example. All right, we're going to say we've got this 500-kilogram roller coaster moving at 7 meters per second, let's say 25 meters above the lowest point on the track. Okay, and over here, that same roller coaster is moving at, let's say, 14 meters per second. And I want to figure out how high above the bottom of the track that cart is at that point. Now we said one of the first things we need to do when we're doing a law of conservation of energy question was we had to figure out what kinds of energy were present at the 2 points. Right? The two kinds are kinetic and potential. So up here is this thing above the ground. Okay, so it has potential energy. So I know that initially I've got potential energy. Is it also moving? Yeah, it's got a speed of 7 meters per second. So I know I've also got initial kinetic energy. Okay, at the end, does it have potential energy? we would have to assume so. They wouldn't ask us how high above the ground it was if it wasn't above the ground, right? Okay, and since that's what this question is asking, we have to assume there's some potential energy at the end. And it is moving, so it also has kinetic energy. Okay, what I want to find, the final height, is part of the final potential energy. So I want to get this term by itself. Best way to do that is to leave it here and move something else. What else do I need to move? Right, the final kinetic energy. And since I'm adding it, to move it over here, I should subtract. All right, so I'll be left with this. The initial potential plus the initial kinetic minus the final kinetic gives me the final potential energy. All right, so I'm like a good halfway to the end of this question now. I'm running out of room, but I'm halfway there. All right, now I need to expand this so that all my formulas are present. Okay, so the formula for potential energy is m times g times h, and this is the initial height. Okay, the formula for initial kinetic energy is 1/2 mvi squared. And the formula for final kinetic, which I'm subtracting, is 1/2 mvf squared. And that equals the final potential energy, which is m times g times hf. Okay? That all right with everyone so far? I want to get hf by itself. I want to leave it there. So what do I have to move? I have to move mg. Since I'm multiplying all of those numbers together, I should move it by doing division, right? All right. Now I'm set up. All I have to do is plug in my numbers, and I'll be able to find hf. Okay, now remember, if you're comfortable with it, at this point you could also remove the mass from every term. If you're not comfortable with that, plug in the 500 kilograms we have written as the mass, and you'll get the same number. All right, so plugging in our numbers here then. We have 500 kilograms times 9.81, okay, times the initial height, which was 25 meters. Right, so that's this term right there. Okay. I'm adding that to 1/2 times the mass, which was 500, okay, times the initial speed, which was 7. So that's that term taken care of. Okay, and then I'm subtracting 1/2 times 500 times the final velocity, which was 14 squared. And then I'm dividing that by 500 times 9.81. Okay, and that will give me my final height. All right, so now all we got to do is plug this into our calculator, and we'll get whatever height it is above ground level. Okay, so we will have our 500 times 9.81 times 25. Okay, plus our initial kinetic energy, 0.5 times 500 times 7 squared. Okay, and then we're going to subtract our final kinetic energy, 0.5 times 500 times 14 squared. Okay, and then we're going to divide that by 500 times 9.81. Okay, so we got that our final height is 17.5 meters. Okay, so yes, it's a lot of manipulating. Yes, it's a lot of algebra. But in the end, every law of conservation of energy question is going to work like that. Okay? The only thing that can differ is if you're asked to solve for V instead of H. And we've done a bunch where we've solved for V. Okay? So expect that in the law of conservation of energy part of that worksheet, you're going to run into a couple where you'll have to do this. Right? Are there any questions on any of the other questions on that sheet? Fourteen and 17? Okay, Cam, you had a question?
So, how many marks would this be?
This could be an 8-mark question. Yeah. Okay, and so like show all of your work. Because the worst thing to do on a question like this is show nothing and plug this into your calculator and make one mistake typing it in. Right? Then you go from getting if you'd shown all your work, 7 out of 8 to getting 1 out of 8 for showing your givens and no work, right? So it's, yeah, it is important to show the method as you go along. Caroline. Right, because height's not squared, so I don't have to square root. You're right. Yeah, that's the difference. If I'm looking for v, I've got the square root, and if I'm looking for h, I don't have to square root. Okay, so 14, 15. Okay. So 2 kilogram rock released from a height of 20 meters. How fast is it going if I release it? Its initial velocity is 0. Its acceleration will be 9.81, but its initial velocity is 0. Right? So at the beginning of question 15, I only have potential energy from being 20 meters above the ground. Okay? And then it says, ignore air resistance and determine the kinetic energy, gravitational energy, and total mechanical energy at each of the following heights, 20, 15, 10, and 0. Okay? Now, the first thing we need to do is find out how much potential energy it has at the beginning. Reason for that? Actually, sorry guys, I'm just going to copy that over so I have it to another page here. Come on, camera. Okay, so this question testing a couple of different, well, that's a mess. Anyway, okay, this question is testing a couple of different things. First thing it's testing is if you remember that mechanical energy is calculated by going EP plus EK. All right, now, when I'm releasing this, it doesn't have any what? It doesn't have any kinetic energy. So all of its mechanical energy that it will ever have is in the form of potential energy when I release it at a height of 20 meters. Right? So I'm calculating the mechanical energy just by doing this. Okay? M times G times H. Right? So the mass of this thing was 2 kilograms times 9.81, so that's 19.62, okay, times 20. So we're looking at, what, 300 and something? All right, stop guessing. 2 times 20 times 9.81. Okay, 392.4. All right, so we've got our initial mechanical energies, 392.4 joules. What's the mechanical energy at all of those heights that the question asks about? 392.4 joules. Remember, this is the law of conservation of mechanical energy. It means it doesn't change. What does change is how much of it is potential and how much of it is kinetic. All right? They ask us to calculate all of those values on the way down. All right? So what I would have to do then is go back to this equation and go, all right, this is always going to be 392.4, and that's always going to equal m times g times h, okay, plus ek. Since I always know what h is, it's the thing they gave me in the question, I can always calculate the potential. How will I get the kinetic? Dom? I don't need to separate the speed. I only need to find the kinetic energy. If I know this number is 392.4, and I can always calculate what this number is, how do I get EK? Right. So always go mechanical minus potential, and you'll have the kinetic. Everybody follow? Okay, so for at 15 meters, for example, or sorry, let's do the 20 meter one. Here's the 20 meter one. Mechanical energy is 392.4. Potential energy is 392.4. Kinetic energy is 0. All right. At 15 meters, we'll go 392.4 minus 2 times 9.81 times 15. Okay, that'll give us our kinetic energy. All right. All right, there's my potential energy. Okay, so I would write that down as the first thing, and then I would go 392.4 minus, whoops, not negative, minus the answer. Okay, and there's my kinetic energy, 98.1. All right, does that make sense? So we're just going to do that like 4 times for all the different heights. Okay, so all that question is asking is, do you remember that? Okay, EM equals EP plus EK. All right, and then for, you said 17? Is that right, Alex? Okay, 17 is just like the one we did earlier. Okay, EI equals EF, but you're solving for V instead of H. Okay, she runs off a platform, so she has she's got kinetic energy. She also has potential energy because she's 10 meters above the ground. But when she hits the water, she has no what? What's your height when you hit the water? 0, right? So she has no potential energy at the end. So this one's setting up like this. EP initial plus EK initial equals EK final. Right? And you can solve for V. She has no potential energy if she's down to a height of 0 at the end. All right? Figured out from there? Okay. Any other ones, I guess? Dom? Okay. Okay. Number 14, also very much like the one we did this morning. Okay, we've got the pole vaulter on the ground. On the ground, moving at 9 meters per second. She only has what kind of energy at that point? Kinetic. All right, so her initial energy is kinetic. Okay. At her maximum height, how fast is she going? 0, right. At her maximum height, she's moving at a speed of 0, so she only has potential energy. Okay, so from there, we should be able to solve for what her final height is. Right? Rather than do the whole thing, I think that should give you a good start on it. Okay. Any other ones, guys? All right, let's get to work on that and get as much of that one done as we can. All right, next week's going to be a busy week.